Hello everyone and welcome to day 1 of Unit 6. We're getting close to the end of derivatives. We're looking at the applications, and the applications for this unit are going to be optimization, related rates, and whatnot, but for now we're going to look just at motion. And so definition of speed is how fast an object is moving without regard to direction. Velocity is how fast an object is moving and in what direction. So if it's positive or negative, it's telling you whether it's moving forward or backwards. To get velocity, you're going to take the rate of change of the particle actual movement. So if you take position and divide it by time, distance over time, you're left with velocity. If a particle is stopped, we know that the velocity is equal to 0. And then instantaneous speed is the absolute value of the particle's instantaneous velocity. Of course, speed does not mean anything with direction, so you take the absolute value of it. And acceleration, the rate at which the velocity is changing, we're already at distance over time. And if you divide by time again, and if you remember acceleration is meters per second squared, well, this is where it comes from. If you multiply by 1 over time, you get distance over seconds squared, and that's where you're going to get acceleration. It's a derivative of the velocity. So just as, so that's where that comes from. Total distance. The total distance is the position at the beginning of the interval and the end of the interval, and anywhere v equals 0, and then add up the differences. So for example, if I'm moving from 0 to 2, stop, move backwards from 2 to 5, stop, and move forward from 5 to 7 and stop, I need to add up this complete distance, how much I move forward, plus how much I moved backwards, but still making sure it's positive when I add it, and then how much I move forward again. I'm going to add all these up. I'm not going to worry about that was negative to get my total distance. And displacement, just figuring out, displacement was where we would talk about this being negative, and you're just going to take the beginning and end points. So if we look at this, the regular position functions, s of t, f of t, it doesn't matter. Derivative gives us velocity. Second derivative, or derivative of the velocity, gives us acceleration. So let's go right into it. S of t equals t cubed minus 6t squared. That's the position function along an axis. Find where a particle is at rest. If we know it's at rest, we know that v of t, try that again. V of t equals 0. And if it's moving left, we know that v of t is less than 0. And if it's right, we know v of t is greater than 0. Left would be going backwards, right is going forwards, therefore positive, negative. So s prime of t equals v of t, which equals 3t squared minus 12t. And I'm going to take v of t, set it equal to 0, which implies that 0 equals 3t parentheses t minus 4. So we're going to get t equals 0 and t equals 4. And so this is where it's at rest. So if we want to look, we can go rest at t equals 0 and t equals 4. Then we're going to do a number line and figure out where it's positive or negative. Negative gives us a negative and a negative, so positive 1, positive, negative, negative 5 would give us both positives. So we're moving right from negative infinity to 0. Again, first derivative, we'll use close brackets, or 4 to infinity. And we're moving left from 0 to 4. Now, if we look at the next part, it says, is it slowing down or speeding up of the same function? So, speeding up. Speeding up, if we look at a graph, this is something speeding up, right? We start out slower and it's getting faster. This is where it is concave up, and we're increasing. Slowing down, the opposite, starting fast, slowing down, concave up still, but decreasing. Now, don't think that this is the only way, we can also look at a concave down, but be decreasing too. So if we look at concave down, we're speeding up here too, right? We're going slowly and then fast. And the opposite way here. If I go like this is concave down, but increasing. What we notice is that the signs of the first derivative and the second derivative for speeding up, the signs of first and second derivative are the same if we're speeding up. If we're slowing down, okay, signs of both, that's an and, not an addition sign, are opposite. The nice thing about that is we don't have to, we can just say it's slowing down because f prime and f double prime have opposite signs. Now, I used up a decent amount of room there, but we're going to take the second derivative here. And we knew the first derivative was 3t squared, so now we're at 6t, and we're at 12. We take the second derivative, set it equal, t equal to 0, that t equals 2, and do our number line. It's negative here and positive here. So what we are going to do now is we're going to combine our two number lines. Sorry for the very poor straight lines. When we go back up, we're at 0 and 4. We're negative, positive, negative, positive. And if we look at this, we know that the signs are the same and if you want, you can, keep going with those lines there. This is our first derivative, and I probably should have color-coded that for you guys. That's our second derivative. We're slowing down. Sorry for the poor penmanship, computer slowing down again. We're slowing down from negative infinity to 0. And this is looking at second derivative, so we're open brackets. See how we are at, let's see if I can get some positive, 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 negative, 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 negative. So we're slowing down between negative infinity and 0, where they're opposite signs, and 2 to 4. So, or 2 to 4. We're speeding up. Where the signs are the same. 0 to 2, or 4 to infinity. Take a minute to look at that. You could also, if you wanted to, make sure you bring that 0 down there. So 0, 2, and 4. So again, slowing down, opposite, speeding up, the same signs. And I like to do the number line to look like this. It's just easier for me. Number 3. What I would like you guys to do is find the derivative, second derivative, and find where we're moving left, right, where it is at rest, and then speeding up or slowing down, and I'll come back with the answer for this one. So again, finding where the particle is at rest, derivative equal to 0, left, right, number line, and then speeding up and slowing down, you need to find second derivative and combine them. So I hope that you guys got these answers. Took the derivative, we got the particles at rest at time of 2 and 5, due to the fact that the derivative equals 0. We were moving left and right at those spots. Then found the second derivative. I combined the number lines. Please look at that and make sure you understand it. I kept the second derivative in red, the first derivative in black, and then we found out where we were speeding up and slowing down. So that's not the entire question. The entire question states that we need to determine the total distance traveled by the particle from 0 to 6. Oh, one other thing. Notice here, t is greater than or equal to 0. Please make sure that you realize that we are moving right starting at 0. So we're not at negative infinity due to this restricted domain here. So just please make sure to realize that. So we got distance traveled from 0 to 6. So distance So what we need to do is, on the number line from 0 to 6, where did we stop? Well, we know we stopped at 2 and we stopped at 4. So what we need to do is figure out the distance traveled from 0 to 2, 2 to 4, and 4 to 6, and then make sure we add them all together. The only way to do that is to find f of 0 or s of 0, s of 2, s of 4, and s of 6. So I'm going to do that right now. We would do that just by plugging in 0, 2, 4, and 6 into the equation. And so the correct mathematical way to write this now is the distance traveled from s of 2 minus s of 0, the absolute value of that, plus the distance traveled from s of 2, or s of 4, excuse me, minus s of 2, absolute value of that, plus the distance traveled from 6 minus 4. This one there? I don't think so. And so we know that that distance was 52. That distance is 27 and 17. And so we know the distance here is 52 plus 27 plus 17. And we get 54 and 52, 106 units traveled. Okay. For this one, I know it's a trig function. Notice that you're given v of t here, so please take a moment to pause it, find the acceleration, and then how do we find where the particle's at rest? Take this and set it equal to 0. And so here should be the answer, the derivative of negative sine 2 pi t. Take the derivative of the outside cosine, negative still stays there. Keep the inside the same, times the derivative of the inside, 2 pi. So we're left with that. The 1, of course, goes away because it's a constant. Second one, when we set equal to 0, there's an important thing here. When you have 1 equals sine 2 pi t, the question that you look at is, when does sine equal 1? When does sine of x equal 1? And we know sine of x equals 1 right there. It's the y value at pi over 2. But you can't just look at pi over 2. You have to look at it every time we go around. So it's pi over 2 plus 2k pi. Well, 2k pi, if we add pi over 2 pi, we get 5 pi over 2. We get 9 pi over 2. And so therefore, and we could keep going, 13 pi over 2 and 17 pi over 2. So that's when sine of x equals 1. The thing that we need to do now is set the inside to be equal to pi over 2, 5 pi over 2, 9 pi over 2, because that's what t needs to be to make that equal to 1. So I'm going to take the inside, what we're looking for the sine function of, and set it equal to each of those. And notice that when you solve, I get 1/4, I get 5/4, and I get 9/4. Well, when you go back, you have a domain between 0 and 2. And notice that 9/4 is larger than 2, and so therefore we exclude it. And the final two answers are 1/4 and 5/4. That's a time. Difficult concept. Please make sure that you relook at this and try to understand it, because this is one that you guys always struggle on. To finish off the notes, what we are going to look at is Rolle's theorem. We already looked at. If the endpoints are the same, then we know that at some point the derivative must be equal to 0, meaning max or min. So the endpoints being the same, meaning that the slope between those two endpoints is 0. The mean value theorem states that if you take the two endpoints, find the slope at some point on the curve, the tangent line is parallel to the secant line.